Bismillahirrahmanirrahim. So here we have a problem. Random variables x and y have the giant PDF given below. Fx comma y, x comma y is equal to c multiplied by x plus y, while x is greater than or equal to 0 and less than or equal to 1, and y is greater than or equal to 0, less than or equal to 2, and this is 0 otherwise. So find the following: the constant c, expected value of x and variance of x, expected value of y and variance of y, covariance of x and y, expected value of x plus y. X plus y is a derived random variable here, which is a function of x and y, right? So, and the last part f, the variance of x plus y. So before we commence the solution to this problem, let us plot this region of non-zero probability. So we have an x-axis here, our y-axis here, and x is greater than or equal to 0, which means it is the right side of the y-axis, and x is less than or equal to 1. So let's suppose we have a 1 here, right? So it's this line, x is equal to 1. So x is on the left side of this x is equal to 1, and it's on the right side of y of the y-axis. So, and the second constraint here is y is greater than or equal to 0, which means it is above x-axis, right? And y is less than or equal to 2. Suppose we have y is equal to 2 here. So y is equal to 2, less than or equal to, which means below this line. So it is this region, actually, this rectangular region, where this probability is non-zero, right? It's this rectangular region. And the value of the probability, the value of the density function here is a c multiplied by x plus y, right? So let's now begin our solution. So part A, we need to find out the constant c. This is the constant c here, which we need to evaluate. So we know that if we integrate this entire region, then using this density function, then the total probability should be 1. So this double integral from minus infinity to plus infinity, minus infinity to plus infinity, fx comma y, x comma y, dx, dy, it should be equal to 1, right? So let us put the density function here. So c is a constant, it can be written outside, and we have x plus y here, and dx and dy, it should be equal to 1. So this will be the limits for x, and this will be limits for y. So x, as we integrating with respect to x first, so suppose we have a horizontal strip here, right? So x is equal to 0 here, and on the extreme right side x is equal to 1. So limits for x are 0 to 1, and we have the limit for y is equal to 0 to 2 here, y is equal to 0 to 2 here, right? So we need to first integrate with respect to x. So this is a c here, y is equal to 0 to 2, right? And when we integrate with respect to x, this comes out to be 1 over 2 x square plus xy, and the limits for x are 0 to 1, and dy here, and this is 1, right? So now put the value of the limit here. So c and y is equal to 0 to 2, right? So this will be 1 over 2 plus y minus 0 and 0. We leave that out here, and we still need to integrate with respect to y, and this should be 1. So now we are integrating with respect to y. So c, this should be 1 over 2 y plus 1 over 2 y square, and the limits are 0 to 2, and this should be 1. So we can take this 1 over 2 outside here. So 1 over 2 c, and we put the value of y here, right? So this is 2 plus 2 raised power 2, that will be 4, and this is 1. So 4 plus 2 is 6, 6 over 2 is 3, right? So this is 3c is equal to 1. So which means c is equal to 1 over 3. The constant is 1 over 3. So we can put the value of the constant here and write the complete expression for the joint PDF. So fx comma y, x comma y is 1 over 3 x plus y, right? While x is greater than or equal to 0, less than or equal to 1, y is greater than or equal to 0, less than or equal to 2, and this is 0 otherwise. So this gives us the complete joint PDF for random variables x and y. So we're done with our part A of the problem. So let's commence this part B, which is to find the expected value of x and variance of x. So one way to do that would be to find the marginal PDF of random variable x. So the marginal PDF of x, which is denoted as fx of x, can be found out by integrating out the random variable y from the joint PDF. So minus infinity to plus infinity, fx comma y, x comma y here, and dy. So in our case, the joint PDF is known. So the expression for the integral for the marginal PDF will be like this. So 1 over 3 can be written outside here, and x plus y here, right? And we need to integrate out random variable y, so we integrate with respect to y here. So the limits for y will be from 0 to 2. So 0 to 2. So after evaluating this integral, we can find the marginal PDF of random variable x. Once we find the marginal PDF, we can proceed to find the expected value of x. So expected value of x will be given by this integral from minus infinity to plus infinity. This is x here, fx of x, and dx here, right? And similarly, the variance of x is defined an expectation like this, x minus mu x square, right? This is the second central moment. So this is expected value of x here, right? So x minus mu x squared, and its expected value will give us the variance of x. And this can be again be calculated using the marginal PDF. For example, we can calculate it using an integral like this, minus infinity to plus infinity. So x minus mu x square fx of x and dx here. So this integral will give us the variance. Another way to calculate the variance would be to use this formula here. So variance of x is equal to expected value of x square minus square of the expected value, right? So there are a number of ways to actually calculate the variance. So using either of these methods here to calculate the expected value and the variance of x, we first need to determine the marginal PDF of x. But all these parameters or functions can also be calculated using the joint PDF. Expected value of x or expected value of x squared can be calculated using either the marginal PDF, or these can be calculated using the joint PDF. So instead of deriving the marginal PDF, let's calculate the expected value of x and the variance of x and the central moment of second moment of x using the joint PDF. So for example, expected value of x from the joint PDF is given by this double integral, minus infinity to plus infinity, minus infinity to plus infinity for y, and this is for x and this is for y. we have x multiplied by fx comma y, x comma y, dx and dy here. So the limits for x and the limits for y here, and we have an x here, and the joint PDF is 1 over 3 into x plus y. So 1 over 3 can be written outside here, and x plus y here, and dx and dy. So limits for x are straightforward, 0 to 1, and limits for y are 0 to 2. X is 0 to 1 and y is 0 to 2. So this will be 1 over 3, y is equal to 0 to 2, x is 0 to 1, this is x square plus xy and dx dy. So this should be 1 over 3, y is 0 to 2. So let us first integrate with respect to x now. So this will be 1 over 3 x cube plus 1 over 2 x square y. So limits are 0 to 1 here for x, and this is dy here. So this is 1 over 3, 0 to 2, y 0 to 2. We put the limits here now. So this is 1 over 3 plus 1 over 2 y minus 0, 0. We leave that out, and we still need to integrate with respect to y. So this will be 1 over 3. Let's now integrate with respect to y now, right? So this will be 1 over 3 y plus 1 over 4 y square, while limits are 0 to 2. So this should be 1 over 3, and put the limit here now. So this is 2 over 3 plus 4 over 4. So 4 over 4 should be 1, minus 0, 0. We leave that out. So this should be 1 over 3 into 5 over 3. So 2 over 3 plus 1 is 2 over 3 plus 3 over 3, that is 5 over 3. So it means that expected value of x, or mu x, is equal to 5 over 9. So we have calculated the expected value, or the mean value of x from the joint PDF instead of first calculating the marginal PDF here, right? So likewise, the variance of x can be calculated using either this formula here or this formula here. This way it can be derived using the marginal PDF, or this can also be derived using the joint PDF function in fact. So we can use this formula here also to calculate the variance of x. So expected value of x square again can be calculated either using the marginal PDF or the joint PDF. So let us do that using the joint PDF now. So expected value of x square is given by integral similar to this one, but instead of x here we put x square, right? So this is 1 over 3, and the limits of x are 0 to 1, and limits of y are 0 to 2. We have x square here, x plus y, dx and dy. So this is 1 over 3, limits of y are 0 to 2, and that of x are 0 to 1. We have an x cube here, and x square plus x square y, dx dy. So this is 1 over 3, limits of y are 0 to 1, sorry, 0 to 2, limits of y are 0 to 2, and we are now first integrating with respect to x. So this will be 1 over 4 x raised to the power 4 plus 1 over 3 x cube y, and the limits of x are 0 to 1 and dy here. So this will be 1 over 3, right? 0 to y 0 to 2, and we substitute the limits now. So this will be 1 over 4 plus 1 over 3y and a dy here. So this is 1 over 3. Now we integrate with respect to y, right? So this is 1 over 4y plus 1 over 6y square, 0 to 2. Let's put the limits now. 1 over 3. So this will be 2 over 4 plus 4 over 6 minus 0, we leave that out. So this is 1 over 2 and this is 2 over 3. So this should be equal to 1 over 3 into 1 over 2 plus 2 over 3. So 1 over 3, the LCM should be 6 here. So this is 3 plus 4, right? So 1 over 3 multiplied by 7 over 6, that is 7 over 80. So expected value of x square is 7 over 18. So using this value here in this formula, we can find the variance of x. So variance of x, also denoted sigma x square, is given by 7 over 18 minus 5 over 9 squared, 5 over 9 squared, right? So this is given by 7 over 18 minus 25 over 81. So this can be calculated using with the help of a calculator. So 7 over 18 minus 25 over 81 is given by 13 over 162. So 13 over 162. So the variance of x is given by 13 over 162. So we have calculated both the expected value and the variance of x using the giant PDF instead of first deriving the marginal PDF of the random variable x. And our next part is to find out the expected value of y and variance of y. Part C is expected value of y and variance of y. So the expected value of y and variance of y can be calculated like in the case of the random variable x, either by deriving the marginal PDF or directly using the joint PDF of random variables x and y. So in case if we are interested to find the marginal PDF of random variable y, so marginal PDF of y, which is denoted fy of y, is given by this integral from minus infinity to plus infinity, and we have fx comma y, x comma y, and we need to integrate with respect to x here to integrate out the random variable x, right? So in our case this will be fy of y will be equal to, the limits for x will be 0 to 1, 0 to 1, and our PDF is, giant PDF is 1 over 3 x plus y, and we need to integrate with respect to x here. So if we evaluate this integral, we get the marginal PDF of random variable y. We can then use this marginal PDF to find out the expected value of y and the variance of y. However, we can also calculate the expected value and the variance of y using the joint PDF. So for example, the expected value of y is given by this integral also. from minus infinity to plus infinity, minus infinity to plus infinity. So y fx comma y, x comma y, dx and dy. So this is limits for x are 0 to 1 and that of y are 0 to 2, and we have y here, and the joint PDF is 1 over 3 into x plus y. So 1 over 3 is a constant, can be written here. So x plus y and dx and dy. So limits of y are 0 to 2 and we have 1 over 3 here. Limits of x are 0 to 1, right? So this will be xy plus y square dx dy. So this will be 1 over 3, right? Y is equal to 0 to 2. Let's now integrate with respect to x, right? So this will be 1 over 2 x square y plus 1 over this will be x y square simply. So this 1 over 2 is because of x square here. So 1 over 2 x square y plus x y square, and the limits will be from 0 to 1 for x, and we still need to integrate with respect to y. So 1 over 3 y is 0 to 2. Now let's put the limits here. So this will be 1 over 2 y plus y square and dy. So this is 1 over 3, and this will be 1 over 4 y square plus 1 over 3 y cube, and limits are 0 to 2. So this will be 1 over 3. Now let's put the limits. So this will be 4 over 4, which is 1, and 2 raised to power 3, this is 8 over 3 minus 0, right? And this is 1 plus 8 over 3. So this is 3 over 3 plus 8 over 3, this is 11 over 3. So 1 over 3 into 11 over 3. So the expected value of y, or mu y, is 11 over 9. So the variance of x is given by, variance of y is given by expected value of y squared minus square of the expected value of y. So expected value of y square can again be calculated either using the marginal PDF or the joint PDF. So instead of driving the marginal PDF, let us calculate the expected value of y square using the joint PDF. So it will be the same integral like this one here, just we replace y with y square now. So variance of y is given by 1 over 3, y is equal to 0 to 2, and x is equal to 0 to 1, and we have a y square here, x plus y dx dy. So this is 1 over 3, y is equal to 0 to 2, x is equal to 0 to 1. This will be x y square plus y cube and dx and dy here. So this is 1 over 3, y is equal to 0 to 2. We integrate with respect to x now. So this will be 1 over 2 x square y square plus x y cube, and the limits for x are 0 to 1, and this is dy here. So this is 1 over 3 y 0 to 2. Let's put the limit for x. So this will be 1 over 2 y square plus y cube and dy here. So this is 1 over 3. Let's now integrate with respect to y. So this will be 1 over 6 y cube plus 1 over 4 y raised to power 4, and the limits of y are 0 to 2. Let's now put the limits. 1 over 3, so this will be 8 over 6 plus 16, 2 raised to power 4 is 16, 16 over 4 here, right? So this will be 1 over 3, this is 4 over 3 plus 4. So this will be 1 over 3. So this is 4 over 3 plus 4. This is 16 over 3. 4 over 3 plus 4. Sorry, this is 4 can be written as 12 over 3, right? So this is 12 power 4, 16 over 3. So 1 over 3 multiplied by 16 over 3. So that is 16 over 9. So the we are calculating the expected value of y square. So this is a mistake here. This is expected value of, not variance of x, this is expected value of y square. So variance will be calculated by calculating this expected value of y square here, putting in here, right? So expected value of y square is 16 over 9. So we can now substitute this value here in this formula to find out the variance of y. So variance of y is given by, this is also denoted like sigma y square, and this is expected value of y square, which is 16 over 9, minus square of the expected value of y, which is 11 over 9. So 11 over 9 squared. So this will be equal to 16 over 9 minus 121 over 81. So this LCM will be 81. So 9 into 9 is 81, 16 into 9 is 144 minus 121. So this should be the variance of y, which is sigma y squared, should be equal to 4 minus 1 is 3, 4 minus 2 is 2, 23 over 81. So this gives us the variance of y. So we have calculated the variance of x and variance of y, and the expected value of x and the expected value of y using the joint PDF of the random variables x and y, instead of first deriving the marginal PDF of random variables x or y, right? So we are done with part part C of the problem also. So next we need to find out the covariance of x and y, right? This covariance of x and y. So this is part D now, covariance of x and y. So the covariance of x and y is given by, it is also denoted as sigma xy, and it is given by expected value of xy minus product of the expected value of x and the expected value of y. We have already calculated the expected value of x and expected value of y. We just need to find out the expected value of xy. This is also known as the correlation of x and y. So correlation of x and y is also denoted by rxy, is given by expected value of xy, right? So let us calculate this correlation now, and we put the value here to find the covariance of x and y then. So the expected value of xy is given by this integral from minus infinity to plus infinity, minus infinity to plus infinity. So xy here, and this is multiplied by the joint PDF, which is 1 over 3 into x plus y. 1 over 3 is a constant, it can be written outside, so x plus y here, dx and dy here, right? So this is given by 1 over 3. In our case, the limits of x are 0 to 1 and y is 0 to 2, right? And this is x square y plus x y square dx and a dy here, right? So this is 1 over 3, limits of y are 0 to 2. We now integrate with respect to x, so this will be 1 over 3 x cube y plus 1 over 2 x square and y square, and the limits for x are 0 to 1 and dy here, right? So this is 1 over 3, and limits for y are 0 to 2, and we put in the limit for x here, so this will be 1 over 3 y plus 1 over 2 y square and a dy here, right? We now integrate with respect to y, so this will be 1 over 6 y square plus 1 over 6 again y cube, and the limits are 0 to 2. So this is 1 over 3, and 1 over 6 can be taken out like this. 2 raised power 2 is 4 plus 2 raised power 3 is 8, right? So this should be 1 over 3 into 1 over 6 into 12. So this is 2 over 3. So the expected value of xy, or correlation xy, is 2 over 3. As this is non-negative, we can conclude that x and y are not orthogonal. X and y are not orthogonal, right? We can also now substitute this value here to find out the covariance of x and y, right? So covariance of x and y, covariance of xy, also denoted by sigma xy, is given by expected value of xy is 2 over 3 minus product of the expected value of x and the expected value of y. So the expected value of x we found out was 5 over 9. So this is 5 over 9 multiplied by the expected value of y. So expected value of y we found out was 11 over 9, right? So 11 over 9 here. So this is equal to 2 over 3 minus 55 over 81. So the LCM should be 81, right? So 3 into 27 is 81. So 27 into 2 is 54 minus 55. So that should be minus 1 over 81. So the covariance of x, y, sigma xy is minus 1 over 81. So we can conclude that x and y are correlated and negatively correlated. So x and y are negatively correlated, which means that when x increases, y decreases, and vice versa, right? So we are now done with part D of the problem also. So let's go on to calculate the expected value of x plus y. So this is part E now, expected value of x plus y. Note that x plus y is a derived random variable. Let w is equal to x plus y. So w here is a derived random variable which is a function of x and y. So one way to calculate the expected value of this derived random variable w, which is x plus y, will be to first derive the probability model, the PDF of the random variable w, and then calculate the expected value. However, as we know that the expected value of summation of random variables is a linear function, so it can be written like this: expected value of x plus y. It can be directly calculated without first calculating the probability model of this derived random variable w. So this will be expected value of x plus expected value of y. So we have already calculated the expected value of x to be 5/9. So this is 5/9 plus the expected value of y, which was calculated to be 11/9. So this is 16/9. So expected value of x plus y is 16/9. In a similar manner, we now need to calculate the variance of x plus y. Part F. Variance of x plus y. Again, we can either calculate the derive the probability model for x plus y, derived random variable x plus y, and then we can calculate the variance of x plus using the derived model, or we can use a formula like this. So variance of x plus y is given by variance of x plus variance of y. We have already calculated that, plus 2 times the covariance of x comma y. We have already calculated this also. So we can just put in the values here now. So variance of x, we found out the variance of x was 13/162. 13/162 here, right? So 13/162 plus the variance of y. So we found out the variance of y also. So the variance of y was 23/81. 23/81. 23/81. And the covariance of x and y we just calculated was -1/81. So this is minus 2 into 1/81. So as we can see, 162 is twice that of 81. So the LCM can be 162 here. So this is 162. So it means we have a 13 here. So 81 into 2 is 162. So 23 into 2 is 46. And we have a minus 4 here, right? So 46 minus 4 is 42. 42 plus 3 will be 45, plus 10 will be 55. So we have 55/162. So the variance of x plus y is 55/162. So we have calculated the expected value and the variance of the derived random variable x plus y without first calculating the probability model of the derived random variable x plus y. So this concludes solution to our problem.